Assalamualaikum warahmatullahi wabarakatuh and good day. So in this video, we will learn a last subtopic for chapter 6 and last for this semester. Alright, so 6.3 is generalized likelihood ratio test. So basically this is a general method that you can use to derive the test of hypothesis. So from previous video you have learned, you have a Neyman-Pearson lemma, isn't it? And then before that you have a general hypothesis testing lah. Alright, so for the generalized likelihood ratio test, okay, the procedure works for simple and composite hypothesis. Okay, so in previous video you have learned what is simple and what is composite hypothesis. So but this one similar we can use for both. Okay, this one for simple and composite hypothesis, whether other parameters with unknown values are present. Okay, so if you look at the definition of likelihood ratio test, okay, define lambda by, okay, lambda equal with likelihood function of omega theta divided by likelihood function of omega. So this one equal with maximum likelihood function of big omega. Okay, this is for population, this is for sample. Okay, and then divide by maximum likelihood omega with this value. Okay, so a likelihood ratio test of H0 equal with omega element in actually this one you can say omega not element, this omega 0 is element in this omega versus alternative hypothesis omega A element in omega population. Okay, so this is just notation. Okay, if you look here, this is consider population, this is for sample value. All right, so this one hypothesis testing test employs alpha, lambda as a test statistic, and the rejection region is determined by this one. So if you look this video with previous video or this test with Neyman-Pearson lemma is quite similar, but the notation is different. Previously we have K, but now we have not K. Previously we have summation yi or y bar y, alright, less than equal with K, but this one we have lambda. Okay, we denote as a lambda, but similar things, which is lambda is considered a test statistic and rejection region is lambda less than equal by K. Alright, so you look example 10.24, page 550. So suppose that y1, y2, yn constitute a random sample from a normal distribution with unknown mean and unknown variance. Okay, so you can see this random sample follow normal distribution, mean mu, variance sigma square. We didn't know the value. Okay, so and we want to test H0 mu equal to mu naught versus HA is mu greater than mu naught. Okay, so you can see here you have H0 and HA alternative. So the solution is, okay, so you know that omega, okay, big omega, the parameter that you have for normal distribution is mu and sigma square. And then notice that omega 0, okay, is the set of mu naught, okay, omega naught is the set of mu naught sigma square, and then sigma square is greater than 0, okay, because variance should be greater than 0. And then you have omega A alternative, okay, it's mu and sigma square, whereas mu greater than mu naught and sigma square greater than theta, greater than 0. Okay, how do you know this one? It's come from here lah. Okay, you know that mu equal to mu naught. Okay, but alternative, the mu is greater than mu naught. Okay, this one. But you have the same parameter lah. Here mu naught, sigma square. Here mu and sigma square. Alright. So hence, the big omega, okay, this omega, general omega, you will have omega naught union with omega alternative, which is you have the same parameter, mu and sigma square. And then you have mu greater than equal with mu naught, okay, because this one we have equal, this one without equal, but then you can have like this, okay, and then here sigma square greater than 0. Now, the constant value of the variance sigma square is completely unspecified, okay, we didn't know the complete value, but it's unspecified lah here. So we must now find maximum likelihood omega hit naught and like maximum likelihood omega hit. Okay, so for normal distribution, okay, you know that the density function of normal distribution is this one. Okay, but this one has been summarized for sum of, okay, because we have y1, y2 until yn. If you look previous video, okay, when we find maximum likelihood of certain parameter like this one actually is a combine, or you find a joint density function of that distribution. So you have normal distribution, okay, so you should know the PDF. So this PDF given in appendix, and then you have y1, y2 until yn. So basically you will have L theta ni. For example, you will have what? F mu sigma, okay, times F. This is for 1, 2 until n. Okay, because you have until n. So this one has been summarized. Okay, actually from previous video you can see as well. So here, because both are unknown, so that's when you can say that this one you have n times. This one sigma square you have n times. But this one we have divide by 2 because we bring the square to this. Okay, to here. Okay, if you look PDF function of normal, this one will be here as well, but here we separate it. Okay, and then we have exponent power negative yi minus mu square divided by 2 sigma square. Okay, this is summation from 1 until n because we have n times. Okay, so then restricting mu to omega naught, okay, then implies mu equal to mu naught. We can find maximum likelihood function for omega naught hat. Okay, if we determine the value of sigma square that maximize the function, the likelihood function, subject to the constraint that mu equal to mu naught. Okay, so I'll show here. Okay, if you remember from example 9.15, okay, we can see that when mu equal to mu naught, the value of sigma square that maximize likelihood function is this one. Okay, actually you have this lah. Can you see the difference? Okay, because we have sigma squared naught, so here we have mu naught. All right. Next, when maximum likelihood omega hit 0 is obtained by replacing mu to with mu naught and sigma square with sigma squared naught hit, then this function will give you this one. All right. So if you have this one, then you will substitute the value of, you can see here, we have sigma naught, okay, this one sigma naught, okay, but here it's become n over 2, okay, so you will have this finally, okay, you can see that 1 over 2 square root 2 pi power n, this one, and then here exponent power n over 2, okay. So now, okay, turn to finding maximum likelihood omega hit. Okay, if you look as in example 9.15, this one we done in previous video. So it is easier to look at ln likelihood function. Okay, so that's why from this equation, the likelihood function, you will take the ln of the maximum likelihood. So when you make it ln of the likelihood function, you will get negative n over 2 ln sigma square. Okay, this one. And then you have negative n over 2 ln 2 pi. Okay, this one. And then this one, you have 1 over, actually this one, what is it? This one. Okay, so that's why this is just the summarize, but this one you will get this one when you ln it. Okay, you get the same thing. Okay, but negative value. And then you take derivative with respect to mu and sigma square. So this one, with mu, this is sigma square. So when you differentiate this one with respect to mu, you get this answer. And then you differentiate with this one with respect to sigma square, you will get this answer. So again here, you must understand how to differentiate. Okay, so this one, recall back your previous knowledge. Okay, previous knowledge in basic maths and so on. All right. So next, we need to find the maximum of likelihood function of this one over the set of this one. Okay, so notice here, you can see that the first one, this one, okay, this is the first one, this is the second one. If you look the first one, okay, if you look the first one, if it's less than 0, okay, if mu greater than y bar, if it's give you equal with 0, it will be mu equal with y bar, and then if it's greater than 0, mu will be less than y bar, okay. So thus, over the set omega, which is this one, okay, we mentioned previously, and then ln mu, okay, and also this one will maximize at mu hat where y bar if y bar greater than mu naught if y bar less than equal to mu naught. So how is it? Actually, you can see from here, okay. So if this one give to 0, okay. So if you look carefully, okay, this one, when you look equation number 1, okay, after you differentiate, you equal with 0, okay, then you look what you get. So in this case, you can see either less than 0, okay, and then equal with 0 or greater than 0. So this one will less than 0 if our mu is greater than y bar. This one will be equal with 0 if mu equal with y bar, and then greater than 0 if mu less than y bar. So from here, then you look which one is maximized at mu greater mu hat, okay. So it will be maximized if y bar, okay, greater than mu or y bar less than mu. So this one, isn't it? So you can see from here, you will get mu naught. Here you will get y bar. So this one actually you get from this equation, okay, when you do the calculation. So just as earlier, the value of sigma square in omega that maximize the likelihood function of these two parameter is this one, isn't it? From here, okay. Then the likelihood function for omega head is obtained by replacing mu with mu head and sigma squared with sigma squared head. All right, this is the same thing that we done for this one. Okay, similar thing. All right, and then when you substitute the value, and then make sure that you have lambda. Okay, this is from the theorem likelihood ratio. This one. Okay, what is lambda? So lambda will be likelihood function omega naught head divided by likelihood function of omega head. So here you can see that you will get sigma head squared over sigma squared naught power n over 2. So this one will give you what is sigma squared, and sigma squared is come from here. Okay. So then you have this one, and then this is for y bar greater than mu naught. This one when y bar less than with mu naught. Okay. So here notice that lambda is always less than or equal to 1. Actually, the lambda value is greater than 0, less than 1. Okay. So the small value of lambda are those less than some k less than 1. Okay. Because of this issue. All right. So if k less than 1, it follows that the rejection region lambda will be less than 1 as well. Or sorry, less than. This is equivalent with this equation. So do you remember this one you done for the Neyman-Pearson lemma? All right. So you have this one lambda less than k 2 power n. So this is considered k prime. So this k prime equal greater than this value. Okay, and then we have this one finally. Okay, so this is what you get lah. Okay, k prime greater than 1 over something. All right, so then we will continue with this one. Inequality in turn is equivalent to this equation. Okay, so you can see that here we try to rearrange, okay, this equation into this equation. Now instead of k prime, we have this one with equal k double prime. Okay, so k double prime, we have n minus 1. Okay, you have put n minus 1. Okay, because we break the this one. Okay, this one we can simplify. Right, here is come from here, this one here, but here you have actually you rearrange, okay, you get n minus 1k double prime, and then you have here as well because you can cancel it out. And then because y bar greater than mu naught, okay, and then you can see that this one happened when lambda less than k and k less than 1. So you will get this equation, all right, which is this one. It's come from here. Okay, you can see here square, square. So that's why it's become finally square root here, and then you square n. Okay, y bar minus mu naught over s. Okay, so there are many steps which is skip here. Okay, but you can try from here to here, and then from here to here. Okay, so here the s ni, if you square, it's become this one. So basically here it will be square root of this one. All right. So notice that if you look this one, okay, this one is a T statistic employed in previous section. Okay, so consequently, the likelihood ratio test is equivalent to the T test of section 10.8. So here we can see that this ratio test that we done is equivalent with the T test because of this one. All right. Okay, so I'll stop here for example 10.24. Okay, however, I will try this test apa ni, again, this example. Okay, because this one there are skip many things here. Okay, maybe you cannot see clearly. Then I will try discuss again by using very detailed step. Okay, and then next video I will continue with theorem 10.1, 10.2. Thank you, class.